Hello guys, welcome on Tesla Adventures. In this video today, we are going to discuss the solutions of test number 3, and we already know that the syllabus of this test is SHM and waves. So this first question, you can see that there is a rod of mass m and length L. It is hinged from this point, and there is another particle of mass small m which is rigidly attached to the rod at the other end. There are two springs of spring constants K1 and K2 which are attached to the rods at these points, and this complete arrangement is being kept on a frictionless horizontal table. We have to find out the frequency of vibration of this system. So let us discuss the scenario. Let us see that first of all, when we will displace this rod from the original position, then this point, we are assuming that the displacement is very small. So we are assuming this as an angular SHM, and we are calculating the restoring torques. So this point is being displaced by a distance of b into theta. We know theta is equal to arc upon radius, and arc is equal to theta into radius. And this point, the other point, this spring is being compressed by this amount, and therefore it would apply a force F1. And this lower spring is being stretched by this amount, and this is x2. So x2 is a into theta. Okay, so you can see that this torque generated by the F1 is in the clockwise sense, and the torque generated by the F2, this will be applying a pulling force, is also in the clockwise sense. So the total torque generated by these forces is F1 into A, which is this distance, in fact F1 into B, and plus F2 into A. So total torque is F1, where F1 is K2 into x1. X1 is b theta, so this is b square theta, plus F2 is K1 into a theta into a again, so it would be a square theta. So this total torque will be equal to I alpha, and the moment of inertia about the hinge, let us first of all take out the common theta, and this is K2b square, this is K1a square, and the moment of inertia about this hinge would be ml square plus ml square by 3 into alpha. Okay, so theta into K2b square plus K1a square is equal to m3m plus m into L square by 3, and alpha is omega square theta. Cancelling this theta with theta, so we can see that omega is equal to option A. In fact, we have to find out the frequency, so it is equal to option number A. Now let's move on the next question. In this question, you can see that there are two identical sources that are moving parallel to each other, these two, and they are separated by a distance of d, and they are producing sounds of frequency f, and they are moving with the constant velocities v0. Now there is a observer which is observing these two sources, and it is located at this point, and initially these two sources are at a infinite distance from this observer, and finally they approach to infinity. So we have to find out the correct graph relating the beat frequency observed by the observer and time. Obviously this observer would observe some beat frequency due to the fact that the frequency observed by these two frequency observed by the observer, which is emitted by these two sources, would be obviously different, and due to these two different frequencies it would observe beat frequency. Now you can see that if we draw a simple line connecting them, then we can see that this source is not moving on the line which is connecting this source and observer. So we have to find out the component of the velocity along this line. So let us suppose that this angle is theta. So in this case, this component would be VO cos theta, and the frequency observed by observer emitted by this S1 would be V upon V minus VO cos theta, okay, into F. So you can see that if this distance is approaching to infinity, and we can also say that cos theta is this x upon this. So if this theta, if this x approaches to infinity, then theta approaches to 0. So if x approaches to infinity, theta approaches to 0, and cos 0 is 1. So f1 initially will be Vf upon V minus Vo. Okay, and f2 initially, which is the frequency observed by the observer emitted by the S2, would be Vf upon V minus Vo, and this would be the constant frequency because there is no angle, it is moving on the line connecting them. And finally, when they are moving to infinity, again this beat frequency, you can see that these two frequencies are same, and the beat frequency is 0 initially, obviously, and finally when they would approach to infinity, again these two frequencies would become same, and the beat frequency would become 0. So the correct answer is obviously option C, because initially also beat frequency is 0, and finally also beat frequency is 0. Now we move on the next question. In this question you can see that there is a point source of power 50 watts. This is the power, and it is producing the sound waves. The velocity of the sound wave is 330 meters per second, and the density of air is 1 kilogram per meter cube. At a distance r is equal to under root of 330 meter from the point source, we have to find out the pressure amplitude. So let us see that we know that intensity is equal to power upon 4 pi r square, and intensity is delta P naught whole square upon 2 rho V, where this is the delta P naught is the pressure amplitude. Now you can see that delta P naught whole square upon 2 into rho is 1 and V is 330 is equal to power is 50 pi divided by 4 pi, and r square is 330. So cancelling this pi with pi, 330 with 330, this is 25. So delta P naught will be equal to 5 Newton per meter square. So the correct answer is B. Now let's move on the next question. In this question you can see that there are two progressive sound waves. One is this and one is this, and they are produced near an ear of an observer. When these two sounds are sounded together, then observer will hear. Now first of all, we know that the frequency of these two is different, and the 2 pi f1 for the first wave is 100 pi, and therefore f1 is equal to 50 hertz, and 2 pi f2 for the second wave is 102 pi, so this frequency f2 would be equal to 51. So beat frequency would be equal to 1 hertz first of all. And the second thing is the intensity after superimposition. So we know that A max is A1 plus A2 okay, and A minimum is A1 minus A2. So you can see that A max is 16 and A minimum will be 8, and the intensity I max square upon, or I can say that I max upon I minimum would be equal to A max square upon A minimum square. So it would be 4:1. So the ratio of maximum intensity to the minimum intensity would be 4:1. So the correct answer would be option D. Now we move on the next question. In this question, you can see that there is a stationary source of sound which emits a frequency Fs. So it is emitting a frequency Fs like that. The speed of sound is C, and there is a wall which is approaching this stationary source with a constant speed of u. So the number of wavefronts reflected by the wall. So the number of wavefronts reflected by the wall is obviously the frequency, and the frequency observed by the wall, F wall, will be in this case we will consider wall as observer, which is moving towards the source. Therefore the frequency observed by the wall would be V C plus U upon C into F, and this frequency is reflected by the wall. And in the second case, when wall is reflecting the frequency and source is observing it, in that case wall is the source and source is the observer which is at rest. So F observed would be equal to C upon C minus U into F wall. So if we substitute the value of F wall, so it would be, you can see that it would be C plus U upon C minus U into F. So this is the number of wavefronts reflected by the wall, which is option A, as well as the reflected wavelength received by the stationary observer in front of the wall is this. So we know that in the first case the wavelength received by the wall would be the true wavelength, because in the first case source is not moving, and source the wavelength depends on the motion of the source and not on the motion of observer. So if source is not moving, then the wavelength observed by the observer will be the same as the wavelength of the sound which is emitted by the source. Now when the wall is reflecting back this wavelength, then obviously wall is source, and now source is moving. So the wavelength observed would be the relative velocity of the sound with respect to the source divided by the true frequency or the frequency observed by the observer. So the sound is coming back with the speed of c and source is at rest. So the relative velocity of sound with respect to source is c, and this f observed is c plus u into f upon c minus u. And you can see that c by f is nothing but it is lambda naught. So this is lambda naught into c minus u upon c plus u. So the correct answer is A and C. Now we move on the next question. In this question, you can see that there is a uniform stick of mass m and length L. It lies on a frictionless horizontal surface and it is pivoted at this point P, which is at a distance of x from the center of the stick. This spring is initially relaxed, which is connected to this rod at this point, other end, and the spring constant is K. Now this complete arrangement is being kept on the horizontal frictionless table, and this stick is given a small displacement. Then we have to find out the value of x for which the frequency of oscillation is largest. First of all, we have to do this. So we know that obviously when we would tilt this rod like that, then this distance displaced by the point at which spring is connected is if this angle is small angle is theta, then this distance is x plus L by 2. So this displacement is x plus L by 2 into theta, and the spring force F would be equal to k x plus L by 2 into theta, and the torque acted by this force on the rod about this hinge point would be k into x plus L by 2 whole square into theta, and this torque would be equal to I alpha, and k x plus L by 2 whole square into theta is equal to I alpha, where I is the moment of inertia of the rod about the hinge. So about hinge we can write down the moment of inertia as m L square by 12 plus x square into omega square theta. We can write down the alpha as omega square theta and cancelling this theta with theta. Omega square is k by m into x plus L by 2 whole square upon L square by 12 plus x square. And if this term is maximum, then this frequency is maximum. Let us now maximize this term. So let us see that what we have to maximize. Let's suppose that z is equal to this term, this one. So this is x plus L by 2, x plus L by 2 whole square upon denominator is L square by 12 plus x square. This is L square by 12 plus x square. So dz by dx, which we have to maximize, we can differentiate it with respect to x. So using u by v rule, we can say that L square by 12 plus x square into 2x plus L by 2 minus this is x plus L by 2 whole square into 2x, and equating it to 0 divided by L square by 12 plus x square to the power 2. So you can see that this is L square by 12 plus x square multiplied by this is 2x plus L minus this is x square plus L square by 4 plus 2xl. In fact, this is xl, and it is multiplied with 2x. So you can multiply these terms and you can equate it to 0. So you can see that it is L square by 6x plus L cube by 12 plus 2x cube plus x square L. It is equal to 2x cube plus L square x by 2 plus 2x square L. So you can see that cancelling this term, we can see that we can make a quadratic equation in x square. So this is x square L plus L square x by 3 minus L cube by 12 is 0, and this would be 12x square L plus 4 L square x and minus L cube is equal to 0. So this is the quadratic equation, and now x is equal to minus 4L square plus minus under root this is 16L square plus 48L this is L to the power 4. So this is L to the power 4 and 48 L to the power 4 divided by 24 L. So x is equal to minus 4 L square plus, obviously we can ignore the negative sign, the root which is coming with negative. So it is 8L square divided by 24L. So this is equal to L by 6. Now we know this is the answer of this one is L by 6. This is L by 6. Now we know that we have to find out the value of this omega also. So we can substitute the value of x as L by 6. So omega square is equal to, there is under root also obviously. So omega square is equal to k by m into x plus L by 2. So this is L by 6 plus L by 2 whole square divided by L square by 12 plus L square by 12 plus L square by 36. So this is 1 plus 3, which is 4 by 6, and it is 2 by 3. So 4 by 9 L square divided by, this is 1 plus 3, which is 4 by 36. 4 by 36 is 1 by 9. So this is L square by 9. So cancelling L square with L square, omega will be equal to under root of 4k by m. So the correct answers are B and D. Now we move on to the next question. In this question you can see that there is a ball of mass 2m which hangs with a string which is attached to this block of mass m, and this block is attached to a spring and that spring is attached to the roof. The whole arrangement is in the state of equilibrium, and this mass 2m is being pulled down by a distance of x naught. Now for x naught equal to 3 mg by k, the maximum tension in the string is 4 mg. So we know that at the instant when this block is pulled down, this ball is pulled down, then at the extreme position this spring would be applying the force, maximum force on the system, and this system will have maximum acceleration. And in the case of maximum acceleration, the tension acting in this rope would be maximum. It is due to the fact that this tension would be balancing out this 2 mg as well as the pseudo force acting on this mass. So we can what we can do that we can see that if this is stretched down by additional wire distance of 3 mg by k, the total force that is applied by the spring on the system F is 6 mg, and the acceleration of the system in the upward direction A would be equal to 6 mg minus mg, which is 3 mg, divided by total mass of the system, which is 3m. So A will be equal to g. This is the acceleration of the system, and the tension acting in this rope would be T minus 2 mg is equal to 2 ma. So T will be equal to 4 mg because A is also equal to g. So the maximum tension is 3 mg by is 4 mg if x naught is 3 mg by k. Now if x naught is greater than 3 mg by k, then the minimum tension in the string is mg. Now let us analyze this situation. We know that this system is in equilibrium. Now let us draw another diagram. We can see that we can assume these two blocks as a system. So the mass of this system is 3 mg. So let us, for instance, let us assume that they are as a system. So this is the natural length of the spring, and the equilibrium position has a extension of x naught which is 3 mg by k. Now we have pulled down this system by a distance which is greater than 3 mg by k. X is greater than x naught. So obviously this is the mean position also. So this system will go up by a distance which is greater than x naught. Okay, so when this system will go up at a distance which is greater than x naught, so in this case the spring will be compressed and it would be pushing down. So now we know that in the actual question there is a block of mass m and a ball of mass 2m. So actually this spring would be applying a force on the block in the downward direction, and this is the rope. Now this block, if we draw the FBD of this block, then a force would be applied by the spring in the downward direction as well as mg would be acting on the block in the downward direction. Now if we analyze that, if this block was alone, neither this rope would be there nor this ball. So if this block was alone, then its acceleration A would be A1, let's suppose. It would be greater than G because the force acting on the block is greater than mg. And if this ball was alone 2m, then its acceleration would be G, obviously. So we can see that this acceleration A1, A2 would be G. So A1 is greater than A2, which means that this rope will slack down and therefore the minimum tension would be 0. So this is incorrect. Now the frequency of oscillation of the system is this one for all non-zero values of x naught. This is incorrect because if x is greater than x naught, then we know that this rope will slack, and for some time only spring and block will oscillate, and for rest of the time these two will oscillate together. So we cannot say that the frequency would be this one for the complete motion, and the motion will remain simple harmonic for x naught less than 3 mg by k. So this is obviously correct. If x naught is less than 3 mg by k, then motion will be simple harmonic. And in fact, if x naught is greater than also, if x is greater than also 3 mg by k, then also this motion would be simple harmonic. But in that case, we have to find out the time period by some different technique. So this is not being asked in the question, so we are not discussing that. So now we move on the next question. In this question, you can see that there is a block string system, and there are 3 blocks A, B and C. The mass of A is 5 kg, mass of B and C is 2 kg. And B and C are connected by a rod which is having a mass of 1 kg, and the length of the rod is 1 meter. A wave is transmitted in the rod between blocks B and C, a transverse wave, and in this wave is going forward and in the backward direction. So first of all, we have to find out the time in which this string waves reaches from one end to another end in the forward direction. Now forward direction is the direction in which these blocks are moving. So first of all, let us find out the acceleration of the system. So acceleration of the system can be calculated by the formula net pulling force upon total moving mass, and as you can see that this 5 kg block is pulling the system, so the net pulling force is 50 and the total moving mass is 10 due to the fact that 5 kg of A, 2 kg of C, 2 kg of B and 1 kg of rod. So this is 5 and you can also, let's suppose now let us consider a rod. This is a rod, and this is block C and this is block B. So let us consider a point at a distance of x from point B. So at this point the tension will be equal to ma, where m is the mass behind this point. So behind this point the mass would be 1 by 1, which is the mass per unit length, into x, plus the mass of block B, which is 2 kg. So x plus 2 into A is 5. So this is the tension, 5 into x plus 2. Now we know that the velocity of the transverse wave is under root of T by mu, and the mu of this rod is mass per unit length, which is 1. So V will be equal to under root of 5x plus 10, and this V will be equal to dx by dt, and we can integrate this. So dx by dt is equal to under root of 5x plus 10. So dx upon under root 5x plus 10 is equal to dt, and integrating both the sides, the integration of, we know that the integration of 1 upon root x dx is equal to, this is 2 root x. The integration of 1 upon x is 2 root x. Okay, so this is this integration of 5x plus 10 would be 2 under root of 5x plus 10 divided by 5, and integration limit would be from 0 to 1, and here the limit would be from 0 to t, where t is the time. So t will be equal to 2 by 5 under root of this is 15 and minus this is root 10. Okay, so you can see that if we take out root 5 common, then it is 2 by root 5, and this is under root of 3 minus under root of 2. So option A is correct, and obviously you know that this wave, the velocity of this wave is the function of the rope density and the tension in the rope, and obviously while this wave would be coming in the backward direction, its speed would be same at each instant, and therefore the correct answer is A and B, because it would take the same time in going in forward direction as well as in going in backward direction. So the C option, that the time for which the wave the time for wave to reach from one end to another end is different in forward direction and different in backward direction. So this is a wrong option, and time for the string wave to reach one end to another end in the backward direction is this one. This is also wrong there. So the only correct options are A and B. Now we move on the next question. In this question you can see that there is a small block of mass m. It is fixed at the upper end of this massless vertical spring. The spring constant of the spring is 4 mg by L, and the natural length of the spring is 10 L. Now this system is being dropped from a height of L on the ground, and this system collides with the ground and spring starts to compress. Then we have to choose the correct options. So at the instant when the speed of the block is maximum, the magnitude of the force exerted by the spring on the block is mg. We have already discussed this concept in work energy power, that when in these kind of systems, when the net force exerted, the net force acting on the block becomes 0, then the speed of the block is maximum. So the net force exerted on the block will become 0 when mg would be balanced with the spring force. Therefore we can directly say that option A is correct, because in the case when the speed would be maximum, the block would be in equilibrium position, and equilibrium doesn't mean that it would not be moving. In fact, it would be moving with the maximum speed, but the net force acting on the block would be 0. Therefore we can say that the force applied by the spring on the block is equal to mg, because the net force should be 0. Now as the block is coming down, we have to find out the maximum speed attained by that block. Now obviously we know that we have already discussed that when the block would be in equilibrium, then spring would be maximum compressed, and therefore we can use energy conservation to find out that maximum speed. So we know that from this position the block has been descended down in such a way such that spring is compressed by a distance of x naught, where x naught is mg by k. Okay, this is the equilibrium position. This is equilibrium position, and in this position V would be maximum. So the total distance by which this block has been descended is L plus this one. Now if you substitute the value of this, so you can see that if we substitute the value of k as 4 mg by L, then it is L by 4. So the total height descended by the block is L by 4 plus L. So work done by mg is mg L plus L by 4, and this work done is utilized in partially in spring, which is half k x naught square, as well as partially in kinetic energy of the block. So this is 5 by 4 mgl, and x naught is mg by k, which is obviously L by 4. So this is half, k is 4 mg by L, and this is L square by 16 plus half m v max square. So you can see that this is this is mgl by m5 by 4 mgl minus this is mgl by 8, and this is half mv square v max. So this is equal to 9 by 8, and cancelling this 8 with 8, so v max is equal to 3 by 2 under root gl, which is the correct option. Okay, and now we have to check the option C, which is that fact that till the block reaches the lowest position for the first time, the time duration for which spring remain compressed is this. Now to attempt this question, we should draw the diagram carefully. So we know that starting from the moment when the spring touched the ground, in this case the spring is relaxed. Now this is the relaxed position, natural length, and then spring descended down. This is the equilibrium position, which we have already calculated, x naught, which is L by 4, and finally spring descends down, block descends down and compresses the spring. This is the lowest position. This is equilibrium position, and this is the lowest position. So we can say that this is the amplitude of SHM. Okay, so from starting from this position to this position, this block was this spring was compressed, and the time, let us suppose that this time is T1 and this time is T2. Now T2 we can directly say that T2 is that time for which in SHM this is mean position. So T2 is the time in which block moved from equilibrium to extreme position. So it is T by 4. Okay, so T by 4, T is 2 pi under root m by k. So T2 time is pi by 2 under root m by k. Okay, this is T2. Now we have to find out the time T1 also. For that we have to find out the amplitude. So we know that if we count from the top position where the block was initially, so the total height descended by the block is L. Initially it was L, as well as let us suppose that this is x naught and this is A. So total height descended by the block is L plus x naught plus A. So L plus x naught is 5L by 4. So this is work done by mg is mg 5L by 4 plus A. So we are talking from initial position to lowest position. And this work done by mg is utilized purely into spring force, spring energy, because now the block is not moving, velocity is 0. This is the lowest position. So spring is being compressed by a distance of L by 4 plus A. So this is half K L by 4 plus A square. So this is mg into 5L by 2 plus 2A, and this is equal to K is 4 mg by L multiply by L square by 16 plus A square plus LA by 2. Cancelling this mg with mg, 5L by 2 plus 2A is equal to, this is L by 4 plus this is 4A square by L, and it would be 2A. Okay, so cancelling this 2A with 2A, you can see that 5L by 2 minus L by 4. So this is equal to 9L by 4, and 9L by 4 is equal to 4A square by L. So A square is equal to L square, 9L square by 16, and A is equal to 3L by 4. This is the amplitude. Okay, so amplitude is 3L by 4 and x naught is L by 4. Now let us analyze the situation, that in this situation the block, this amplitude A is 3L by 4, and this position where the block was at that instant when spring just touched the ground and block was in equilibrium, this position was L by 4. So you can see that this is L by 4, so we can say that this is A by 3. So we know that the time taken by the block to move from 0 to A by 3 is same as the time it takes to move from minus A by 3 to 0. So this time we have considered this time as t1. So this time t1 can be calculated by using x is equal to A sine omega t. So x is A by 3 and this is A sine omega t. So cancelling A with A, sine omega t is 1 by 3 and omega t is equal to sine inverse 1 by 3. Omega is 2 pi by t, so t is equal to t, or we can directly we can say that omega is under root k by m. So t is equal to under root of m by k sine inverse 1 by 3. So now let us check that option. So the time which we have already calculated t2 is pi by 2 under root m by k. Okay, and this we have to also substitute the value. So we can substitute the value of k. So the t2 time was pi by 2 under root m by k. So t2 is pi by 2 under root m by k. K is 4 mg by L. Cancelling m with m. So you can see that this is pi by 4 under root L by g. This is t2, and t1 is under root of m by 4 mg by L sine inverse 1 by 3. So you can see that this is pi by 4 under root L by g and this is L by 4g sine inverse 1 by 3. So option C is also correct. Now we move on the next question. In this question you can see that there are two wires which are fixed from both the ends, wire A and wire B. Wire A has some length. Let's suppose wire A has length of L, density rho, tension T and diameter D. So wire B has length 4L, density 4 in fact, I think it is double, yeah. So it is length is 2L, density is 2 rho, tension is 2T, and diameter is 2D. Okay, so now we have to choose the correct option. We know that the frequency of A would be 1 upon 2L under root of T by mu. And let us change this formula. Well, let us use this formula instead. We can write down mu as rho into A, where A is the area of cross section, so rho into pi d square. So this is T upon rho pi d square. So now for B, we know that length is double, so it is 4L. Tension is double, so it is 2T, and density is double, so it is 2 rho pi, and diameter is also double, so this is 4d square. So cancelling this 2 with 2, FB is equal to 1 upon 8L under root of T by rho pi d square. So you can see that FB is equal to 1 upon 4 times of FA. So which means that the fundamental frequency of A is equal to the frequency of third overtone of B, because B has the so FB is 1/4 of FA. So FA is the fundamental frequency, and FA is equal to 4 times of FB. So the fundamental frequency of A is equal to 4 times the fundamental frequency of B, and 4 times the fundamental frequency of B means the third overtone frequency of B. So option C is correct. And we have to talk about the velocities also. So we know that this term is the velocity, and there is a factor of this is 2, which is coming out from this term. So we can say that the velocity of wave in the B is half of the velocity of wave in A. So the correct answers are C and D. Now we move on the next question. In this question you can see that there is a spring mass system, and this is spring K2, which is equal to K, and K1 is equal to 2K. We have to find out the time period of a small SHM of this system. Okay, so now we will discuss the conventional method, which we already have discussed in the SHM chapter. That let's suppose we have stretched down this mass by a distance of x, and obviously I am assuming that this system is already in equilibrium, and beyond the equilibrium position I am stretching this mass down by a distance of x. So obviously this point will also move down. So let's suppose that this point moves down by a distance of x dash. So x minus x dash is the amount by which this spring is being stretched, and I'm assuming that the net extension in this spring is x2. So x minus x dash is x2 obviously, and this point will move up in by a distance of x dash, and this pulley will move up by a distance of x dash by 2. So this spring would be stretched by a distance of x dash by 2, and therefore we can say that x1, which is the extension in this spring, is equal to x dash by 2. Now x dash from the first equation is equal to x minus x2, so x1 will be equal to x minus x2 by 2. So 2x1 is equal to x minus x2, and 2x1 plus x2 is equal to x. This is the first equation. Now we know that this force developed in this complete string would be the spring force of this spring, and the spring force of this spring would be K2x2, and K2 is equal to K, and x2 is x2, and this spring force is 2, let's suppose it is the tension in the rope, and this T and T, 2T is equal to K1 X1. So 2 into T is K2 X2, and it is equal to K1 X1, and 2 K2 is equal to K, and this K1 is equal to 2K. So you can say that x1 will be equal to x2 from this equation, and therefore 3x1 is equal to x, and x1 is equal to x by 3, and x2 is also equal to x by 3. So this is the value of x. Now we know that the force developed in this spring is the restoring force for this mass. So the restoring force for this mass will be K2 X2, and F restoring will be equal to K2, which is equal to K, and x2 is equal to x by 3, and this restoring force is equal to m omega square x. So cancelling this x with x, omega square is equal to k by 3m under root. Okay, this is omega, and we have to find out the time period, so it is equal to 2 pi by t, and t will be equal to, let us use the new page, t will be equal to 2 pi under root of 3m by k. So taking this 2 inside the root, it would be 12m by k, and therefore n will be equal to 12. So the correct answer is 12. Now we move on the next question. In this question, you can see that there is a streetcar which is moving rectilinearly between two stations. Let us draw the scenario. There are two stations. Let's suppose this is A and this is B, and there is a streetcar which is moving rectilinearly between these two stations. On these two stations, the car stops. Therefore, we can say that these are the extreme position, and you can see that the force acting on the car is equal to, F is equal to A minus Bx, where x is the distance from station A. Now this is the net force acting on the car. So let us see that where this force is 0. So it is 0 at x is equal to A by B. So we can see that obviously this is the mean position, and from both extremes the mean position is at a same separation. So we can say that the maximum, let's suppose the small a is the amplitude, so we can say that the maximum separation between both stations is 2a, and 2a, this let us assume this something else. Let us assume that this is a and this is a, and the 2a will be equal to this twice of a by b. So n is equal to 2. So this is the correct answer. Now we move on the next question. In this question, you can see, let us draw the scenario that there are two vehicles, A and B. This is A and this is B, and they are moving towards each other with a speed of u, where u is equal to 25, and they are producing a sound of frequency 550 hertz, and the wind is blowing in this direction, in the direction of A, and the velocity of wind, v wind, is equal to 20 meters per second. Okay, now this vehicle A, the driver of vehicle A hears the sound blown by the vehicle B, as well as the sound which is reflected from the vehicle B. Okay, and the difference between the wavelengths of both the sounds received is this. So we have to find out the value of P. Now let us analyze the situation. Let us see that the wavelength received by A directly by B, so let us name it as lambda 1, where lambda 1 is the wavelength received by A emitted by B. So in this case, the source is moving towards the observer, and therefore we can say that the wavelength received by this A would be something different as per the true wavelength. And to find out that wavelength, what we need to do, we need to first of all find out the frequency received by A. Now A is observer which is moving towards source, and B is source. So the velocity, first of all let us see that the wind is blowing like that, and the velocity of wind is 20 and the velocity of sound is 320. So when B will emit the sound, then sound will travel in this direction and wind is traveling in this direction. So the net speed of the sound will be 300. So we can write down the frequency F1 as 300 plus VO, which is observer's velocity, which is A, and it is I think 25, yes, and in the denominator it would be 300 and minus the velocity of this B. So the velocity of B would be 25. Okay, so this is the, and this is the true frequency which we know. So this is the frequency observed by the A. Now the wavelength observed by the A is lambda 1. So wavelength is equal to the velocity upon frequency. Okay, this is the wavelength. So this is relative velocity of A with respect to sound, and this is the frequency observed by A. Obviously we are not assuming that, we are assuming that there is no effect of velocity of wind on the speed of A and B, as it is given that they are moving with the constant speeds this. So we are assuming that their absolute speed is 25 while A is moving in this direction and sound is coming in this direction with the velocity of 300. So the relative velocity of A with respect to sound will be 325. Okay, and the frequency observed would be 325 F upon this is 275. So it would be 275 upon F. This is the wavelength lambda 1 observed by the A directly emitted by the B. Now let us make the second, let us find out the second wavelength. The second wavelength is the wavelength emitted by A, but it is reflected from B and it is again received by A. So let us find out lambda observed by B. Now in this case you can see that the wavelength observed by B would be the frequency observed by B upon V relative of B with respect to, or I've written, it is V relative of B with respect to sound upon frequency observed by B. Now the frequency observed by B would be obviously, or we can directly just find out the frequency observed by B, which is emitted by A. So it is equal to the velocity. Now when A is the source, so source is moving in this direction, so sound would be moving in this direction as well as wind is blowing in this direction. So the speed of sound would be 340. So it would be 340, and the velocity of this observer, which is B, is towards the source. Therefore there would be a positive sign, and the velocity of B is 25. So it is 25 into F is the true frequency divided by 340 minus 25. So this is 365 F upon this is 315. This is frequency received by B. Now B is reflecting this frequency, and now B is the source of this frequency and A is the observer. So the frequency received by A is, let's suppose, f2. So f2 would be equal to, now again this sound is moving in the backward direction, so the speed of sound would be equal to 300, and plus the speed of observer A is 25 divided by the 300 minus speed of source, which is 25, multiply by the frequency emitted by B, or we can say the frequency reflected by B. So the frequency reflected by B is this one. So this is FB. So this is equal to 325 upon 275 into 365 upon 315 into F. This is F2. And the wavelength received by the A would be V, velocity of A with respect to sound, V relative, divided by frequency received by A. So velocity of A with respect to sound is sound is coming in the backward direction with the speed of 300, and velocity of A with respect to sound would be 325. So it would be 325 divided by F2. F2 is 325 into 365 into 275 into 315, and F would be there. So cancelling this with this, so lambda 2. Now we have to find out the difference of these two frequencies. So we have already calculated lambda 1, which was 275 by F. So delta lambda will be 275 by F is the common factor, and 1 minus 315 by 365. So it would be 275 by F into 350 by 365, and F is 550, so delta lambda will be 275 divided by 550 into 350 divided by 365. This is 5 by 73. So the value of this P would be 73. So the correct answer of this question is 73. Now we move on the next question. In this question, you can see that there is a square plate of side A, and this plate is hinged at one of the corner. This hinge point is suspended about an horizontal axis so that it can perform SHM like that, and we have to find out the time period of a small SHM of this plate about the equilibrium position. Now we know that the time period of this physical pendulum is equal to T is equal to 2 pi under root I by mgd, and I is the moment of inertia about hinge, and d is the distance between hinge and center of mass. So we know that the moment of inertia about COM for the square plate is ma square by 6, and this A is the side of the square, so let us denote the side as B. Okay, and in fact it is given the side is A, so let us use that only. So this is A, ma square by 6, and about this point I hinge will be ICOM plus m into this distance, which is A square by 2. So this is 4 by 6, and therefore it is 2 by 3 ma square. Okay, so this is 2 by 3 ma square, and d is equal to a by root 2. So the time period of a small SHM is 2 pi under root of 2 by 3 ma square divided by mg, and d is a by root 2, cancelling m with m, so it is 2 pi under root of 2 root 2a by 3g. So root n is root 2, and n is 2, and m is 3. So n plus m, we have to find out n plus m, it is equal to 5. So 5 is the correct answer. Now we move on the next question. In this question, you can see that there is a man which is standing in front of a mountain. So let us draw the scenario that this is the man standing in the front of a mountain, and the distance of man from the mountain is x, let's suppose. So man is drumming at a rate of 40 beats per minute. So let us convert this into beats per second. So it would be 2 by 3 beats per second. So this is the frequency, which is 2 by 3 hertz. And he's not observing any echo, which means that the sound which is emitted by this man is going in the forward direction, and it is reflected back from the hill, and it is getting superimposed with the sound which is continuously generated by the man. And obviously he is standing on the node, therefore he is not observing any echo. So let us suppose that there are n loops formed between these two. So nth harmonic is the standing wave configuration. So we can say that 2 by 3 is equal to nv by 2l, and l is x. Now he moves in the forward direction towards the hill by a distance of 90 meters, and the remaining distance now is 90 minus x minus 90. And again he is not hearing the echo when the drumming rate is 60 per minute. 60 per minute means 1 hertz, and again he is not hearing the echo, which means again he's on the same mode, but he's not hearing any echo. So which means that he's again standing on the node. So we can say that it would be 2 into x minus 90. So if we compare NV, so we can see that 4 by 3 x is equal to 2 into x minus 90, and 4 by 3 x is equal to 2x minus 180, and 180 is equal to 2 by 3x, and x is equal to 270. So we have to find out x by 10. So x by 10 is equal to 27. So the correct answer is 27. Now we move on the next question. In this question, there is a source S which is at rest, and there is a receiver R which is also at rest. The frequency generated by this source is F, and this frequency is being observed by R directly, and it is being reflected by the wall, and then it is being observed by R. So obviously these two frequencies which are observed by R would be different, and the difference of these two frequencies would be the beat frequency. So we have to find out that beat frequency. So let us suppose that the frequency observed by R directly would be F1, and we know that there is no relative motion, or there is no motion of S and R, therefore this frequency would be same, true frequency F. And we have to find out the F2, where F2 is the frequency reflected from the wall. Now let us assume that F wall is the frequency observed by the wall, and when wall is moving away from the source, then obviously wall is considered to be the observer, and the formula would be V minus U upon V into F. And when this wall will reflect this frequency, then F2, which is the frequency received by the receiver, and in this case source is wall, and wall is moving away from the observer, and observer is at rest, so it would be V into F wall, because the frequency reflected by the wall is F wall, divided by this is wall is the source and it is moving away, so divided by V plus U. So V upon V plus U into F wall is V minus U upon V into F. So cancelling V with V, F2 will be equal to V minus U into F upon V plus U. And if we find out the difference of these two frequencies, then the common factor would be F, and V plus U minus V minus U upon V plus U. So it would be 2UF upon V plus U. So this K would be equal to 2. So the correct answer of this question is 2. Thank you.